Great. Thanks everyone for your patience. I think it's time to get started. So welcome to this webinar today, hosted by Decodable. And we're going to talk about the top 5 mistakes deploying Apache Flink. Your presenters today are Robert Metzger. So Robert is one of the co-creators of Flink and is a staff software engineer on the team at Decodable. And we also have presenting Eric Sammer, who is the CEO at Decodable and author of many books and kind of quite esteemed in the data community. You help me saying that. Yeah, so there are the contact information is on the slide there, so you can get in touch afterwards if you really want to. Robert, if you could just advance the slide. So this is what we'll be talking about today. Robert is going to go into a lot of detail about the mistakes that you can find when you're deploying Flink. And then Eric's going to kind of round that off with, once you've got over these problems and you have Flink running, what can you do? So some of the common patterns that we see in stream processing, particularly with SQL. And then we'll have Q&A both at the end of Robert and Eric's session there. So if you haven't done a Zoom webinar before, there is a Q&A button. Drop your question in there, and then I'll kind of be doing the triage on that. I'll look through those and we'll either answer them online, we'll type in the chat window, or Eric will take them live. So with that, I'm going to hand over to Robert to get us started.
Thanks a lot for this nice introduction, John. I'm really excited to spend a few minutes today with you to talk about some common mistakes that I see over and over again when people are like not on day 1 using Flink, but on like day 2 or day 3, where they have figured out like a use case, implemented it, and then they get into the weeds of deploying it. And I want to clarify some of these common mistakes and explain some of the underlying principles behind Flink that help understand these issues. And a very popular mistake number 1, is that data serialization is expensive. So when you're choosing your data types in your Flink implementation, I often see people using things like Java hash maps, sets, or other collection data types, or other custom date representations for representing their workload, like their events. And these data types are stored in our state storage in Flink, so usually in RocksDB or on the heap, and also used for network transfers. So the serialization happens in the data exchange between task managers and also between the sources and sinks. It happens when accessing RocksDB, even if RocksDB is not spilling to disk, so if RocksDB is only relying on in-memory caches, it still needs to transform the in-memory representation on the heap onto the memory representation in RocksDB's in-memory cache for like memory pages. And also locally, Flink sometimes cannot just hand over objects on the heap. It also sometimes sends data via network buffers locally. And besides the data involved, it's also CPU expensive to do serialization. So let's take a look at an example that is particularly bad, but it shows you how easy it can happen that you make a mistake. And in this example, the author apparently wanted to represent coordinates in events, like a start and an end event, where the start has coordinates and the end has coordinates, and they're representing this via a Java hash map. So there are 2 keys, a start key and an end key, and then there is this location POJO with the coordinates. And when you're serializing this with Flink, then Flink doesn't know how to efficiently handle a hash map. It knows how to handle strings or tuple types or the SQL types or Afro. These types are extremely efficient to handle in Flink. But for like standard Java collection types, Flink falls back to an external serialization framework. In case of Flink, in the current versions, we're using the Cryo framework. And Cryo will basically serialize these hash map events like here. So the first entry that it will write to the data stream is an integer, the size of the map, so 2 in our case. Then it will write the key of the first entry, which is start. And then it will write the type of the value, and that's a location type. And then it will write the fields. And then it will write the second key, again, the type and the fields. And if you're looking at this roughly takes 120 bytes of data that is transferred over the wire or written to disk for every event. This is quite inefficient if you consider that you could also use a POJO that is optimized for the use case, which has basically just 4 integer fields with the start coordinates and the end coordinates. And representing this in memory is just 16 bytes of data. So it's like a 7.5x reduction in data size, both over the network and also what you're storing on disk or in memory in RocksDB. There's a very extensive blog post on the Flink blog about tuning the Flink serialization framework. It's a fairly advanced implementation that allows you to use lots of different serializers like Afro, as I mentioned before, the built-in serializers of Flink. They're very powerful. They're able to, for example, access key fields from binary data without needing to deserialize the entire event. So Flink knows which portion of the binary data on the network is the key for doing a shuffle, and then it will just deserialize the right bits from the stream instead of deserializing everything. So that's the first common mistake that can give you a very bad performance penalty in terms of network traffic and CPU utilization. A second mistake, or something that I just sometimes think people should be aware of, is that Flink doesn't always need to be fully distributed. Like, you don't need always multiple machines running in a distributed fashion. Flink has something included that is called the mini cluster that allows you to spin up Flink locally in one JVM, and this will include everything that you know from distributed clusters. So you can use RocksDB in this context, you can use checkpointing in this context, the web UI, SQL, all the connectors, everything. It's the same components, but instead of them running in a distributed fashion across multiple machines, they're just started in the same JVM. And setting this up is fairly simple. So this is the code that is required to get Flink going. So basically, once you're executing this cluster.start method, you will see a lot of output from the JVM, like a lot of log output from the JVM, where you see all the components of Flink starting. And the use cases for this mini cluster is, for example, local debugging and performance profiling. So if you are running into an issue in production and you really don't understand what's going on, then you can just start Flink. I mean, just depending on how easy you can get your data locally. But given that you can get your data locally and everything, you should be able to very elegantly step through the Flink code, the framework code, and your own code to understand why something is not working the way you expect it to work. And the same goes for profiling. So we've talked about the serialization stack. And if you're unsure whether your serialization stack is actually causing some performance issues, you can also use the mini cluster locally, like run Flink for 10 minutes locally, attach a profiler, do some sampling over the most common code paths, and then you hopefully see, I don't know, Cryo showing up on the top or Afro showing up on the top, so that you understand what's going on and you can easily fix it. Another very important aspect of well-written software is testing. And with this mini cluster, you can very easily bring up Flink in your integration tests or end-to-end tests. You can even bring up Kafka, for example, or MinIO as an S3 replacement if you want to test against with checkpointing or with Kafka under failure scenarios. And I can also recommend you the test container project, which allows you to start these auxiliary components also in the same JVM in your tests. And there's a third use case that I quite like, and that is for processing very small streams efficiently. So even in production scenarios, the mini cluster can be a viable option because it's exactly the same components that you would use on a fully distributed cluster. But sometimes if it's just a few hundred messages per second, you don't need a full cluster. It's sometimes fine to just use a single JVM. So the next topic is maybe not a mistake, but more an advice. But let me quickly see, there is a question about the mini cluster and the lack of documentation for mini cluster. So that is something where I'm not aware if there's a lot of documentation pages about it. There's certainly very extensive use of the mini cluster in the Flink tests. If you want, you can just import the Flink project into your IDE and then search for usages of the mini cluster class. And then you'll find many, many scenarios, also specific scenarios that simulate certain errors, inject configuration parameters, and so on in the Flink integration tests. But I can also follow up with you after the talk if I find some additional documentation for the mini cluster. All right, so the next topic I want to talk about is the different ways of deploying Flink, because this is something where I think that Flink is perceived as difficult to use, but actually it's quite beautiful once you understand how it works, because there are so many options, and it is quite flexible how you can deploy Flink. And I'm trying to give you a framework to think about the deployment options of Flink. So there are different execution modes, like ways how Flink gets the job to execute. And one execution mode is the so-called session mode. Session mode means that multiple jobs share a job manager. So in my example here, 3 jobs are sharing the same job manager. This is only recommended in specific scenarios. For example, if you have many short-running batch jobs or very small streaming jobs, and the resource costs of running a job manager for each job are too high. In almost all cases, I would recommend using the application mode by default. Application mode means that you have one job per job manager instance, and this one job is planned on the job manager instance. There's also a per job mode that is deprecated as of Flink 1.15 and only used in the yarn context of Flink. And the difference between these two modes is that in the per job mode, the job graph is generated in a separate JVM. So you start the Flink client computes the execution plan and submits it via RPC to the job manager. In the application mode, all this happens in the same JVM. So the job manager comes up, executes the user code, which generates the job graph, which is like a logical execution plan, and then it starts processing. The benefit of this application mode approach is that you don't have any issues with class loading, and there's just fewer moving parts in your infrastructure. Like things that belong together are executed together. So these are the execution modes. So basically, you only need to remember session mode and application mode is the default. Unless you really know what you're doing or you know that you have a very specific use case, you can always go with application mode by default. Now, the deployment options. there are basically two types of deployment options. Passive deployment, where the Flink resources are managed externally. It's also called standalone mode in Flink. And then there's active deployment, where Flink actively manages the resources. Let's first talk about the passive deployment or standalone mode. Basically, you have a bunch of JVMs that are deployed wherever you want. You can use the scripts that are included in Flink, and these scripts will just launch Job Manager and Task Manager JVMs. They will connect to each other and they will start processing. You can do the same on Docker. So you can just bring up a bunch of Docker containers and they will find each other, do the processing. Or you use what almost all, but everybody is using these days, and that is Kubernetes. You define two deployments, one for the Job Manager, one for the Task Managers, and they will do the processing. The benefit of this passive deployment is that it supports Flink's reactive mode, which is basically autoscaling. It supports many DIY scenarios. So you can also use your homegrown deployment system. And it also allows for fairly fast deployments because all components are starting up together at the same time. But you have to take care of some infrastructure things yourself. For example, restarting failed JVMs is up to you. So if you're just deploying on bare metal, you have to make sure that the processes are restarted in case of a failure, and also stuff like log management, like log file management and so on. On the other hand, there's active deployment, where Flink actively manages its resources. So Flink is started, for example, on Kubernetes or on Yarn, and then it knows how to talk to Kubernetes or Yarn to acquire the resources it needs. And it also knows how to restart resources when they fail. And the benefit of this approach is that if you, for example, have a batch job or batch jobs that have changing resource requirements over the time, like initially they only need like 2 machines, and then they need 10, and then they need 2 again in the end, then Flink will be able to dynamically allocate and deallocate these machines as needed. The downside of this approach is that, in particular in the Kubernetes case, it requires a lot of permissions from Kubernetes. It requires permissions for creating pods and for services. And it's a fairly uncommon pattern on Kubernetes. So I'm not aware of any other system that needs this many permissions from Kubernetes, like no Nginx or Spring Web App needs this much permission from Kubernetes to run there. Usually the default model in Kubernetes is that the system is managed from the outside. Like you decide how many resources to give to the system, like in the passive model of Flink. And Flink will just use all the resources that it has available. So these are, this is my way of thinking about the deployment options of Flink. And I think it's not too complicated. The fourth topic I want to talk about today is properly sizing your cluster. And this is important because I've seen both. I've seen very disappointed people that expected more from Flink in terms of performance or the ratio of resource investment to results. And I've also seen people that have amazing hardware and almost nothing to process. So I just feel sorry for them that they have this much resources and almost, they're basically idle all the time. So to mitigate this problem, I recommend people to get some understanding of their workload and of their environment, and do some basic math to figure out what is like a realistic usage of resources to expect. And I understand it's difficult if you don't know the system, like if you don't know really how it works underneath. But that's why I'm going to have a short example in this talk where I run you through the process of doing like such a back of the napkin calculation to understand a baseline performance for your Flink deployment. And I'm explicitly saying baseline because you need to add like 20–30% of additional resources on top for any spiky loads that could be caused by failure recovery or some change in your user behavior, upstream failures, like your Kafka is going down and is offline for like 2 minutes, and then you need to reprocess much more for a short period of time. So let's dive into my example. It's a very simple topology with a Kafka source, a window operator that is creating a sliding window of like it's collecting data for 5 minutes, and these 5-minute windows have an offset of 1 minute. So you get results once a minute, and these results are written to a Kafka sink. And we're using RocksDB as the state backend for keeping the data of the sliding window. And also a common misconception, RocksDB is not a database that you need to install somewhere, that you need to maintain and connect to and whatever. It's not like MySQL, it's just a library inside our Flink JVMs that is writing to local disks. So it's really, you don't really see anything from RocksDB as a user of Flink. So we have this topology, this Flink job, and our sample data has a message size or event size of 2 kilobyte, which is admittedly quite large. And we have a throughput of 1 million messages per second incoming, and we have 500 million unique keys. This is important for the window operator to determine the state size. And we're checkpointing once a minute. So once every minute, we take a full copy of the state of the data in the sliding window and persist it to an external storage, which is usually S3. And I'm going to assume that we have 5 machines, each machine running a task manager. And I'm assuming that these machines are fairly beefy, as you will see. To do this calculation, I'm going to look at this Flink cluster from a single task manager's perspective. So basically everything we're discussing here is happening 5 times in the cluster, but it's easiest explained from the perspective of a cluster, of a task manager. So as I said, each message is 2 kilobyte and we have 1 million messages per second. So that's a 2 gigabyte per second stream. If we divide this 2 gigabyte per second stream by 5 machines, then each machine is receiving 400 megabyte of data from Kafka. Next, we have, I forgot to mention one thing. So on each task manager, you see here that we have a Kafka source, this key by operation, the window operator, and the Kafka sink. And this might be counterintuitive, but in Flink, each parallel instance in the cluster, so each task manager, is processing one parallel slice of your streaming topology. So if you run this topology in a cluster with parallelism of 5 and 5 machines, then there will be 5 Kafka sources, 5 window operators, and 5 Kafka sinks. And this key by here is actually not really an operator. It's more of a configuration for this data connection here. So each task manager will execute a Kafka source, a window operator, and a Kafka sink. So for this Kafka source instance, we will receive 400 megabyte of data per second. For this connection between the Kafka source to the window, where we key by, so we partition our incoming stream in real time based on some key for the window operator, so that the same keys end up on the same machine in this window operation call. So we have this stream of 400 megabytes of data that is coming, and we are splitting it into 5 machines, which means that each machine receives 80 megabytes of data. So we basically send 80 megabytes of data locally. It will never touch the operating system network stack. It will just stay within the same JVM of Flink. But the 4 other connections are remote. So for 4 times 80 is 320 megabytes of data that we're sending over the network to the 4 other task managers. And of course, we are also receiving data at a rate of 320 megabytes per second to shuffle the data across the cluster. And then we also have 67 megabytes of data on average per second that we are sending to Kafka again because of the window operator that is emitting results once a minute. So now we also need to look at the amount of data that we are producing by the state and the checkpointing, more importantly. So in our case, each machine, so each key in the window is 40 bytes. And we have 5 windows because we have this sliding window approach. So we have 5 instances for every incoming record where we put an update to the aggregate. And for each machine, we have 100 million keys. That makes roughly 20 gigabyte of state that we will keep in RocksDB, which is also an important information for sizing your local storage. And if we checkpoint this 20 gigabytes of data every minute, we will have on average 333 megabytes of data that we're sending over the network. As a side note, if we are using incremental checkpointing, then we won't back up the entire 20 gigabyte every minute. It will be less. It will only be roughly the amount of keys that we have touched within the last minute. So if we have only touched 20% of the key space, then we will only roughly back up 20% of the state to S3 or our state storage. Another interesting side discussion that we can quickly do is how much disk access do we actually produce? So we receive 200,000 messages per second on each machine, and each window is 40 bytes with 5 windows. That makes roughly 40 megabytes per second of sustained disk access that we are producing. So when you're sizing your storage in or on Amazon, for example, make sure that your disk is able to sustain 40 megabytes per second of data transfer. So if we add the checkpointing here to our overview of the task manager's machine traffic, then we see that in total, we have 720 megabytes of incoming data and 720 megabytes of outgoing data on each task manager. I've looked up on AWS what you can get on a typical machine. And for larger machines, starting from 16 CPU cores or more, you can get a guaranteed 10 gigabit Ethernet connection. And 10 gigabit is 1,250 megabytes per second. So these machines are able to sustain this much load. These are obviously quite big machines. Like we're talking about 16 cores. They have plenty of main memory and so on. So this could work. But also like a Kafka cluster that is able to sustain such high load is also must also be pretty beefy, because basically the Kafka rate is determined by the disk speed. So each broker would need 400 megabytes of disk speed or less, but then more brokers. Yeah, I think the details don't matter here. What matters here is that now we have some numbers, and based on these numbers, we can discuss what machine types to choose and how to size our cluster appropriately. Maybe 5 task managers is actually not a good idea. Maybe 10 smaller task managers would actually be a better approach for this use case. Also, I want to mention a few things that I have not looked at in this back of the napkin approximation. So I have not looked at protocol overheads from the whole network stack. I have not looked at the internal RPC calls of Flink, also the RPC calls of Kafka, and also the connection with the checkpoint store. The checkpointing causes networking bursts. So I've assumed a constant flow of data being streamed to S3, but in reality, we do checkpoints once a minute. So once a minute, we'll have a spike in load whenever we trigger a new checkpoint. Flink supports asynchronous checkpointing, so the processing will continue while Flink is streaming the latest backup to S3, but still there will be bursts. The same goes for the window emission. As I said, this tumbling window is triggering once every minute. And obviously, when this window is empty, it tries to flush as much as it can to Kafka. Again, this causes network spikes, which will affect all kinds of components in this cluster. And of course, there are potentially other systems in the network that we are not considering in this approximation. And I've also touched on the topics of CPU, memory, and disk access, but they have not been fully considered. I mean, in general, it's for these big use cases, I can strongly advise to do some benchmarking to make sure that everything is well calibrated. Yeah, so that's the cluster sizing. And then we actually come to my final advice, and that is ask for help. Flink has been around for many, many years, 6-7 years, and almost all problems have already been solved online. There's different channels that you can use for getting help. The official old school way is using the users at flink.apache.org mailing list. It is indexed by Google and also searchable through lists.apache.org. But I get that not everybody likes mailing lists these days. There's also Stack Overflow. The Apache Flink tag has a lot of questions and good answers accumulated over time. Very recently, the Flink community has launched a Slack instance for folks that like to interactively discuss their problems. And I mean, in the last 2 years, maybe not that actively, but generally there is a very nice global meetup community where people meet in person in all areas of this world. And also there's the Flink Forward conference, also with training, if you want to get up to speed with your Flink knowledge. And yeah, besides asking in these channels, I would also like to give you the opportunity to ask now if you have any questions about my talk, but also anything else about Flink deployment and operations related questions. So please use the Q&A feature of Zoom to ask me anything, or Eric. I mean, if people need more time to come up with questions, then we can also go ahead to the second part of this event and hand it over to Eric, because Eric's going to basically tell us what amazing things you can do once you figured out all the deployment issues that I've talked about with Flink, like what you can do with Flink SQL.
Appreciate it, Robert. Thank you so much. And again, if you have questions, it's a great opportunity. Feel free to put them in the Q&A section, and we'll sort of monitor those as they come in and make sure that they either get to Robert or to myself, based on the kind of question. And we'll do our best to get to all of them. A couple of people have asked, while I'm sort of sharing my screen, a couple of people have asked, whether or not we're going to have the recording online and the slides will be available. The answer is absolutely. We'll make sure that all of you, I think John can share information about where that's going to be available. John, are we going to wind up putting stuff on YouTube? Is that right?
So we'll put it on YouTube, but also if you've registered for this webinar, you can come back to it and just play it on demand.
Great. So we'll make sure that folks get that. I am going to share my screen. You should be able to see my screen now. Okay, so I am going to show off just a couple of things that you can do with Flink SQL, and again, sort of common patterns that I think we see people running, and sort of like the way Robert described, thinking about the performance profile and the way sort of metrics and sort of data flows through Flink. There are actually a number of really common flavors of pipelines that that we've seen in the wild. And again, I'm going to show them to you via Flink SQL, and I'm using Decodable here, but everything I'm going to show you, you can do with low level Flink SQL. We just have lots of bells and whistles. I'm not here to sort of necessarily sell you on Decodable, so I'm going to blow up my screen a little bit. And just so folks have a little bit of context, I'm using a data generator here for the demos that I'm going to show you. I won't get into a ton of details, but it's basically Envoy proxy data. So it looks like clickstream data. And I'm emitting events once every 100 milliseconds in JSON format. And so like all of the pipelines that I'm going to show you are based on this data. So this connection is outputting to a decodable stream. You can just think about this like a Kafka topic or a Pulsar topic or a Kinesis stream, whatever sort of makes the most sense to you. And so this is what the data actually looks like as it comes out of the generator. So basically it's the simplest schema that you can possibly imagine, right? It's a single field. It contains a string that is the raw, unparsed, Envoy example. And the data generator kind of generates, it's kind of nonsense. It generates, different HTTP methods and different URLs, or different paths at least, and different protocols with different response codes. So it's not necessarily fully realistic, but it's close enough, at least for our purposes. So this is what the data looks like coming out of the processor, out of the generator. Super common to see like log messages this way, or other kinds of source data. You can think of this as being like tweets. You can think about this as being clickstream data. There's financial transactions like Fix and like those kinds of things. And so what I've done here is I have a pipeline, which is decodable speak for basically a SQL query. And this first pipeline is receiving data from that message, from that stream or that topic. And I'm using Flink SQL and a couple of different features here. And Decodable, we have some extra functions that we register with Flink SQL, like grok parsers and those kinds of things. So I'm reading from the stream what Flink would normally call a table. We differentiate between tables and streams, but don't worry about that. So this is our input data, and I'm basically keeping the raw value and using this grok function. If you've never seen grok, it's basically like regex on steroids, to extract a bunch of named patterns, right? So we're going to extract like the timestamp, the method, the path, the protocol, status, flags, and then the response size. And we're going to put that into a map inside of Flink. Now, to Robert's point, because we're using the Flink SQL and the table API, there's more efficient data structures, under the hood that are happening here. But we get to treat it like a plain map, and there's some detail there. So I'm basically taking this raw field and then these extracted fields, which is like a bag of key value pairs. And I'm doing a couple things. One, I'm preserving the raw value so that we can sort of carry it through. So you can think of this as like enriching the data with the extracted data, but keeping the original data available if downstream consumers also want this, which is a pretty common pattern. It's a nice trick to make life easier for some people without losing fidelity or the ability to like go back and reprocess data if you need to do it. So one of the most important things in the world is enriching the data and getting the data types correct, because some of the downstream processing we're going to do with things like window functions require us to have event time extracted. And so here what I'm doing is I'm taking this time field that we've extracted and I'm parsing it as, I think it's RFC 3339 format, which is subset or superset of ISO 8601, whatever. So we have a valid timestamp here, and we're going to be able to use this downstream to aggregate based on event time rather than processing time. So, which is super important for correctness and a bunch of other things. And then on some of these other fields, we're just renaming them, right? We're just, giving them sort of easier names to reference, and we're flattening out that map. We're basically projecting certain fields. If I happen to know all of these are not going to be null, but like we could do things where we handle null values differently and those kinds of things. I'm also promoting or casting some of these fields like status to integers, so we can sort of treat them, the way we would want to in downstream analytics. So again, just really common in general. I think about that as like a parsing or an extraction kind of pipeline. The important thing is that from a workload perspective, to Robert's point, now we have some metrics and stuff here, but you can, if you kind of dig in, you can get a lot of the stuff from Flink under the hood. So like the number of records per second input, the bytes per second input, and then output as well. So this is what's measuring sort of total pipeline, not operator level, the way Robert showed, but just total pipeline or total SQL query, inputs, outputs, those kinds of things to understand, is the pipeline working and those kinds of things. They give you a little bit of a sense of what it's doing. Interestingly, you can see that sort of bytes per second, we are growing the per record size because we're keeping the raw value and we're extracting a bunch of other things. And so, it's super common that like we purposely separate out the sort of parsing and extraction and create a curated stream that has the data the way we want to be able to use it for downstream consumers. It's true that we can like squish a whole bunch of pipelines together or a whole bunch of SQL queries or really complex job graphs into smaller pipelines, but the reason we split it apart is because we want to enable a bunch of different use cases downstream. So we're basically creating a curated, cleansed stream for all of our downstream, pipelines to be able to use. And so again, you get a sense of what these look like. We've extracted a bunch of values so that they're easier to work with. And again, this is our HTTP event stream at this point. And now we have two pipelines that are hanging off of this stream. One that I'm extracting and turning these from sort of like HTTP clickstream into more higher level business events. While I also have another pipeline that's doing some aggregation on HTTP request and response stats. And that's going to show you some windowed aggregation. But this one's simpler. Let's look at this first. To extract product updates. So I'm basically pretending like request to this product URL. I'm going to turn this into what looks like events that tell us which products are being updated. So basically, I'm filtering the HTTP requests where they have this products path, looking for request methods that are post, put, and delete, and where the response status is basically a successful HTTP response. And then I'm maintaining the time on the event, and I'm effectively doing some path extraction. And again, like in production, you'd probably want to be like a little bit more careful about some of the corner cases around bad paths and those kinds of things. But I'm basically splitting on slashes and extracting the second component of the path, which I know is going to be our product ID. And then I'm casting it to a big int and then naming it product ID. For the method, I'm basically collapsing, and this is like a nice use case of case statements and similar things inside of, Flink SQL or dropping down to the table API. Basically taking post and put and then turning them into upserts. These could be, things that modify a product or create a new product. And anything else that I get, I'm actually just going to preserve, right? So I have like one case where I'm specializing this, and then otherwise I'm going to maintain the method, which we know because of our predicate is basically only the delete case. And then I name that operation. And so again, here you can see we're basically outputting like one record for every, or on average, slightly more than one record for every 10. And we can actually look at what's coming out of this pipeline. And what we'll see is that we have these nice, clean, product ID was deleted at this time. And this kind of gives you an idea about how you can sort of systematically enrich and transform data so that something that starts as low level as like a log message or a tweet or like a clickstream event can actually turn into these like business operation events. So if you're building things like customer data platform or product recommendation systems and all these other kinds of things, these kinds of techniques, this systematic enrichment and decomposition of these complex pipelines can actually simplify how you think about the various stages of processing that are happening. I'm going to hop back real quick to our HTTP events. I'm going to show you the other pipeline because this one's a little bit trickier and I think is going to show you something cool. So basically what I'm going to show you how to do here is take the data that we are getting, aggregate it by into sliding windows, exactly what Robert talked about, and then count the number of events by both HTTP path and the response code. And then what we're going to do is we're going to create like an alert or like a trigger off of cases where we're going to see a lot of HTTP 500s or errors. Again, super common kinds of use cases for streaming. Oh, I lied to you. I'm going to show you a tumbling window, not a sliding window. Anyway, so if you've never seen tumbling windows or windowed aggregation in stream processing, it's a little bit like spooky the first time you look at it. It's really not that bad. So basically what we're doing is we're taking our HTTP events data, and I always like to read SQL statements inside out, start from the source and then work my way outward to sort of like better understand what's happening. So we're starting with the HTTP events stream that I showed you. And this tumble function, which is the table value function, is going to take this stream, it's going to produce a table. So we're basically transforming the records as they sort of come out in this function, if you will. But this is really sophisticated windowed aggregation logic or functionality that Flink supports. Robert talked about this a little bit earlier. And basically this function says, okay, so this is our input. Which field in the record do you want to treat as having the event time? And so we're basically telling Flink we're going to use that _time field as the time of the record itself. And then we're going to create a window. We're basically going to look at all the data within a 5-second range, but not 5 seconds from the wall clock, or the time on the server, 5 seconds with respect to the event time, right? That comes out of this time field. So we'll show you more about this in a second. When you use this tumble function or any of these windowed aggregation table value functions, which are documented in Flink docs, there's lots of reference on this, you get these extra columns like window start and window end. And so this is basically a timestamp of the beginning of the window and then a timestamp of the end of the window. And there's at least one other field called window time I won't get into, but it's important to know about. So basically we're going to group by the window start and the end. We're going to group by the path and the status, and then we're just going to count. And we're going to name this count. And so what we should get is every 5 seconds, we are going to get one record for the path and the status and the count. And I'm going to show you what that output. And again, from a workload profile, you can see that we're taking in, 3 about 3K per second, 10 records per second. We're outputting far less than that because we're aggregating, we're reducing the output size of the data set by about a third, maybe 50%. So when we look at the output stream that this is producing, which could be in a Kafka topic or Pulsar or S3, it can be, it doesn't need to be a stream, it could be anywhere. You can see, and I'll expand all of these. You can see what this looks like. So and I'm doing everything in UTC. So this is 18:51:35 to 40 seconds. The home page in our fictitious application got a response code of 422 twice, right? And you can see at the same time, products 2 got a 422 once, and so on and so forth. So basically, we're going to continue to get these events, in these 5-second increments, and I can use all sorts of different time functions that will cause Flink to either retain a bigger window or a smaller window, but to Robert's point, will have a pretty big impact on throughput and all of these other kinds of things. Under the hood, we are doing a lot of sort of fancy stuff to make sure that we're going to be able to handle this workload. The one thing, at least in Decodable, that you wind up controlling is the number of tasks that that this pipeline turns into. And Robert talked about that. Again, I won't go a ton into all the details of like what goes on inside of Decodable, because I want this to be useful information for people who are using Flink, but maybe not Decodable. This one is super interesting and tricky because I get people asking me how to do this. Okay, so I have these windowed aggregates. What I want to do is I want to create an alert, some kind of trigger that feeds like an observability system, or maybe just like feeds like a microservice or something like that, whenever the number of like HTTP 500s starts to look wrong. And so now I purposely picked like a really sort of fancy way of doing this just to sort of show you what it could look like. So I'm using, let me start from the beginning. So I'm looking at the path stats stream that I showed you before. And basically what I'm doing is I'm taking an average of the count for all path and status combinations ordered by the window time. And this is what's sort of interesting. I'm looking at a dynamic 5-minute window that is occurring before each one of those events. So when you look at the current row, imagine the last 5 minutes for that path and status combination. And so it's very dynamic and basically allows you to partition that data or sort of look at sort of each slice of the data over this dynamic 5-minute window. And so if you've never seen an over function in SQL, this is like some of the more advanced functionality that you can get in SQL. So basically getting a rolling 5-minute average. And then I'm looking for only the HTTP 500s, and I'm basically only outputting records where the average is greater than 2.2 event HTTP 500s over the last 5 minutes. And just to show you that this pipeline does what I say it does, we'll look at some output here. And so each one of these is basically acting like alert. So within the 40 to 45 second bucket, we had 2 HTTP 500s within that time, but over the last 5 minutes, it's been 2.33. And so you see those kinds of things coming out the upside, and we're sort of filtering out all the stuff below 2.2. So that gives you an idea. You can create all sorts of stuff that responds to these events out the other side. These are just some of the patterns that we see, sort of like extraction and aggregation, and then like this trigger kind of pattern or alerting kind of pattern. But there's lots of different things that you can do that are really, really cool with Flink SQL, or Decodable if you're using Decodable. I recognize we have a bunch of questions that I want to make sure that we get to. So I'm going to stop here and we'll see if we can knock out some of these questions.
Awesome, thank you, Eric. So I'll just start top to bottom and go through the questions. So the first question is, as for serialization cost, can Flink automatically identify operators that can be grouped together in a single JVM to avoid serialization? And the answer is yes, and this is called operator chaining in Flink. So basically, when you have a bunch of operators that are that have the same parallelism and there's no shuffling in between, then Flink will just chain them together. That's what we call operator chaining. And the output of one operator is the input of the next operator. So we are skipping the entire network stack, everything, and really passing these events through the JVM very efficiently. The next question is about scaling by changing the number of slots per task manager versus scaling by adding more task managers. And if you want a PhD in how to configure Flink, then this is a very important topic of study. Basically, so when I discussed the when I did this back of the napkin calculation for the network throughput of my example, I had this task manager slice, and I had one source and one window and one sink operator running on the task manager. And if you want 2 instances of everything on your task manager, then you can configure your task manager to provide 2 slots instead of 1 slot. And you can go pretty wild with this stuff. So if you have a machine with 16 CPU cores, you can decide to give each task manager 16 slots. So each task manager will run 16 Kafka sources, 16 window operators, and 16 sinks. You can go even crazier. You can also say, I want 2 Kafka sources, but 8 window operators per machine, and then 2 Kafka sinks. And the underlying model that you should think always about is who are the CPU consumers in your job. So if you have like a super long, complicated topology with many operators, and each operator is doing a lot of CPU intensive stuff like matching a regular expression, decompressing data, whatever, then you should over provision your CPUs. Like you should have more CPUs than slots. But if you have some super boring IO heavy pipeline, then you can also have very few CPU cores per task manager and more slots. So basically, slots are a means to controlling parallelism on a machine. The next question is about whether mini-cluster is good for end-to-end tests and for testing customized connectors. And the answer is definitely yes. So if you want to just manually test end-to-end test some custom connector implementation, then the mini cluster is perfect for this. Besides maybe having some specific integration tests that call deep into your methods, but generally mini cluster is pretty well suited for this. Like the resource overhead for having a mini cluster running locally is quite small. So when I tested it with Flink 114 recently, the JVM, like just JVM with mini cluster running, was roughly 60-70 megabytes of heap allocation, which should be fairly reasonable, I think, for such a big system. I mean, the heap allocation goes up if you allocate specific parts. Like if you allocate Flink SQL stuff, then these classes obviously take more memory from the heap. But just an empty Flink cluster is fairly small. Then there's a question about what kind of deployment are you recommending for Flink SQL? Do you still deploy on application mode or session mode? So that's a complicated question with my favorite answer, it depends, because it depends on what you're trying to achieve. So if you want to provide your, let's say, downstream users with an interactive SQL experience where they interactively play around with SQL queries, then using something like the Flink SQL shell, which is like a command line interface for developing SQL queries, connected against a session cluster. Then I think this is the optimal or the best mode of deployment. If you are running a web service and you want to allow users to just submit queries via HTTP, then maybe mini cluster is the right approach. Or if you know that you are only ever going to run like 2 SQL queries in your life and you know exactly what they're going to do, then just using like a main method with application mode and passing the SQL query in there is the right approach. So it really depends on your use case. Everything is possible from an engine perspective. A SQL query is exactly the same as a regular user implemented Flink job. It's just highly optimized by Flink. Next question is about unstructured or schemaless data. Do you have dedicated JSON data type or something like JSONB? So I guess like binary JSON in Postgres. Yeah, so here, I mean, first of all, Flink is like basically everybody's using Flink like this. It's really not uncommon to have schemaless data or unstructured JSON data. It depends a bit. So if you're using Flink SQL, you don't have to worry about this because Flink SQL is just optimizing this for you. So Flink SQL is only sending around the fields that you need at some point. Fields that you will never touch will be kicked out immediately. If you're manually writing Flink jobs in Java, then you have to do this yourself. So basically you have to manually decide yourself which fields to carry around, which fields to extract, how to extract them, when to extract them. Of course, it generally makes sense to only carry around as little data as you need and to kick out everything else as early as possible. You can just instruct the, let's say, Kafka source or Kinesis source to use the JSON parser, and then you will, I think, get like an object node type. And then I would recommend using something like a mapper or so that is chained, and put your stuff into a custom POJO that contains the fields that you need, or a tuple type in Flink if you're too lazy to write your own POJO. Yeah.
And I think even in that case, you sort of still need to defend against, you know, cases where the fields don't exist and all these other kinds of things. So like in general, these kinds of schema-free use cases can be a little bit tricky to handle sort of all the corner cases. But there are definitely ways of doing it. I do think that it's really common.
Yeah. All right. Are there any other questions or follow-up questions based on my answers?
So Liang had a question in the chat.
Yes.
And I think then that'll have to be our time. But I encourage folks to continue the conversation either in the Flink Slack or in the Decodable Slack.
Yeah, so there's this one question about reactive mode in the chat that I can quickly answer. And that's about autoscaling Flink with reactive mode through something like a horizontal pod autoscaler in Kubernetes. And this feature is certainly generally available, in particular as of Flink 1.15. So in Flink 1.15, there has been quite a few important improvements to make reactive mode production ready. Before Flink 1.15, there are some shortcomings, like metrics are not properly working after a rescale event, but with 1.15, this is fixed.
Great. Well, with that, I'll say thank you everyone for attending. Thank you, Robert and Eric. Robert, would you mind just advancing the slide?
Yes. Sorry, I forgot. I should have done this while I was answering.
So just a few things. If you're interested in some of the things that Eric showed, we are Decodable.co, and you can do what Eric was doing for free on the app. We have a lot of docs, and we have a YouTube channel on which this recording will appear. Also, if you just follow the registration link you used to get to the webinar, you'll be able to watch it on demand. But we'd love to see you in Slack and love to hear your feedback. This is the first time we've done this with Robert. And if you enjoyed it, let us know what other things you'd like to talk about, and we'll take it from there. We're very responsive and excited to kind of talk about Flink. We'll be at Flink Forward, and we also do demo days every Thursday. So lots of opportunity to kind of keep the conversation going. And with that, again, thanks to Eric and Robert and you. And that's our webinar. Thanks, everybody.
Thank you.
Bye.